Hello. Okay, so let's start by basically analyzing the orthogonal matching pursuit algorithm. So basically, this is the algorithm that you have uh, implemented in homework 8. And so the idea is that we are interested in basically solving something like this or something like this. And basically, we want the solution x to be sparse. Okay, so we want to minimize the number of non-zero elements inside vector x. And so this is like a very tough problem, and we can solve it in a number of ways. So as you have seen, one way is basically to replace this counter of the non-zero elements, the so-called L0 norm, but we know that it is not really a norm, using the L1 norm. And so this will give you like the family of algorithms like the lasso algorithm and the problem 3 in this homework. Again, it's like, so there are proofs like, that minimizing quantities involving the L1 norm, it tends to produce sparse solutions. And that was a big thing because once you use the L1 norm is indeed a norm, and having it in an optimization problem is basically gives you a convex optimization problem which can be solved efficiently. But in the first part of this lecture, my focus will be on in program 2, which is the orthogonal matching pursuit. While it is still fresh in your minds. And the idea is that you start with, you examine matrix A column by column, and you start like choosing columns based on the inner product of the column and the residual vector. And the residual vector is updated in each stage by subtracting, AX, and X is chosen to be the minimizer of this quantity. And so you keep doing this till the residual is below a certain threshold, and you get your vector x. So what is really going on, and is this algorithm actually converging? So these are like the typical questions that that comes to mind when you see an algorithm. So if it's an iterative algorithm, so is it converging? Okay. And this is like sort of a fundamental question. And then the second question, what is the speed of convergence? So if we are doing steps so in the nth step, is the error basically proportional to 1 over n, proportional to 1 over the cubic root of n, proportional to 1 over n squared. So what is basically, so here the question is about the rate of convergence. Okay, so these again are fundamental questions, and like if you write a paper and you propose an algorithm, an iterative algorithm, people will like ask questions. Reviewers will basically think about this. So, okay, so you have an algorithm, why is it working? Just the checking by a number of simulations is not enough. Okay, perhaps you are lucky, perhaps you are choosing, the values of parameters in your simulations are such that you get convergence, but otherwise you don't have convergence. So the first half of this lecture is basically a quick, so basically there are details written here, and it is a quick attempt to analyze this algorithm. Okay, so and then we'll go back to we finished convergence of sequences of random variables in the previous lecture, and our next topic will be, I assume that you already know Poisson random processes, so our next topic will be renewal processes. But again, the first order of business in this lecture is sort of a quick investigation of the orthogonal matching pursuit algorithm. Okay, so and I actually will do a general version. So here is matrix A, it is n by m, here is vector B, it's like the vector of observations or measurements, and as a matter of notation, I will use A, and I write down a set here. This set basically contains numbers between 1 and m. It's a subset of basically the set from 1 to m, and it means that we are talking about a matrix, a submatrix of A, with columns taken from A, whose indices are basically in this subscript here. right? So if I write like A1 and 2, so this is basically means a matrix whose columns, it has two columns, which are basically the first two columns in matrix A. And then S of k, I will define it as the set of selected indices during the kth step after choosing a new index. Right, so basically we choose a new index in each iteration as you have written in your codes, and we will start with an empty set. And what we do is that there is a least squares problem that you solve at the kth step, which is that you take the known vector A, and then you take basically matrix A, a submatrix of A with those indices that you have been choosing at every iteration, and then you basically try to find Z that minimizes this quantity, right? The L2 norm squared, and so the minimizer will be x of k. So basically this is argmin of Z and basically this quantity here. Basically, the solution, so this is the least squares problem, and we know that x of k will be basically as of k Hermitian, as of k inverse, and then a Hermitian s of k, and then b. Okay, so basically this is the solution using least squares. And let v of k be the index chosen at the kth step. Okay, so at the kth step, this is what you do. Like you go and choose a new column. And how do you choose it? What you do is this: you take the qth column in matrix A, and you take its inner product with the previous residual, and you just scale. So you take the column divided by the L2 norm, and then you compute basically the magnitude of this thing. And you do so for every column in A that has not been selected yet, okay? And so basically the new index that you put in your set S is the maximizer, so it's argmax of Q, and you choose Q outside basically the already, the already chosen columns. And so for the remaining columns, you basically compute the inner product with the normalized column and the residual, and basically you choose the new index to be this guy here. So it's the maximizer of this quantity. Okay. And now again, it's like, why is this algorithm converging? So it's like the residual is decaying. So how can we make a theoretical argument that actually the residual is decaying, and actually it is decaying to a specific value that we will see right now? So here is the first trick in analyzing this algorithm. We will consider an alternative algorithm in which at the kth step, we do not optimize over this vector. Okay, so like in each step, you have one more column in A involved. So what I will do is doing this. I will take the previously selected columns. Now, from the previous step, there is an X that is associated with them. Okay, so basically there is a previous step in which you solve this problem. You get X of k minus 1 as the argmin of the L2 norm squared of B minus A S k minus 1 Z. And here, okay, so this one, so you keep this, you keep those elements. And in the kth iteration, what you do is that you select your new column, okay, and now you will take this vector and fix it. So xk minus 1, you will fix it, and you will just optimize over the coefficient of the new column. Okay, so again, in the original formulation of the orthogonal matching pursuit, what is this quantity here? It's basically the columns that has been selected. Each column is multiplied by a component in Z, and you are optimizing over Z, and Z will have k components in the kth iteration. Now what you are doing here is that you know, rather than having k optimization variables, what you do is that you fix k minus 1 of them, and you just obtain the coefficient that should be multiplied by the new column a sub v of k. So definitely this will not reduce the residual as if you solve the full-blown problem. So again, this problem here, what you are doing here is a special case of the problem above. Here, rather than, again, playing the game with k optimization variables, what we do is that we fix k minus 1 of them, and we just optimize of one variable. While the optimization problem, the least squares problem in OMP is you solve over the whole k optimization variables. Before proceeding, let me say that there are algorithms that actually do like this, because this is simpler. So again, engineering, you have the conventional trade-off between accuracy and performance. And so sometimes you say, okay, so OMP is fine, but it is, you know, it requires more computations than I can afford. So perhaps I can use this trick here to reduce complexity. And of course, there will be degradation in performance. Okay, but I am using this step here as a conceptual step in the analysis. I am imagining that I will just optimize over the coefficient multiplied by the new column. Okay, so my optimization variables are really just one complex variable, and conventional least squares, you differentiate with respect to eta, equate the derivative to 0, and you will get basically the result that alpha, which is this optimal eta, is this thing here. It's the inner product. It's the inner product of the new, so you take the new column, which has an index v superscript k, and you take its inner product with rk minus 1, and you just scale by the L2 norm squared of this vector, and this will be your optimal guy. Okay, now take this value and plug it in. Plug it in, okay? And so this will give you a residual vector. I will denote it R tilde, not R, because in the actual algorithm, we have R of k. R of k is the minimum of b minus ask z squared, where z is in c k minus 1 k, sorry. So basically we have k variables. So this is R of k. So this one I will call R tilde of k, because again of this thing that I will not actually, I will fix actually k minus 1 variables and just solve for one of them. So you plug in, and when you plug in, okay, you will get that basically R tilde of k is related to Rk minus 1, and between them is this orthogonal projection matrix. Okay, and so this is equal to basically this orthogonal projection matrix Rk minus 1. Then you take the L2 norm squared. So what is the L2 norm squared? L2 norm squared of this thing. So the L2 norm squared of this thing will be Rk minus 1 Hermitian, and then Rk minus 1. And this is an orthogonal projection matrix, so it is Hermitian and it is idempotent. So its Hermitian multiplied by itself will give the matrix back. And so you will have something like this. And so you get two terms. You will get Rk minus 1 Hermitian Rk minus 1, which is the L2 norm squared of Rk minus 1, minus, and then you get basically this term sandwiched between Rk minus 1 Hermitian Rk minus 1, which is this result here. Okay, so again, it seems like a weird thing to do, like you imagine a step that actually you do not do in the algorithm itself in orthogonal matching pursuit. So why? This will be basically our next step. Any questions? Okay, so that's the step. You know, it is an upper bounding attempt. Okay, so that's the trick. This one here, like if you optimize over the key variables, you definitely will get the same or a lower residual relative to the fictitious case in which we do not actually do in OMP, in which we fix k minus 1 variables and optimize on the coefficient of the new column in A. Okay, so I am sure basically that if this quantity here comes from a full-scale minimization problem, while this one we fix k minus 1 variables. And so it's always the case that this one is less than or equal to this one, and from the previous page, this one is equal to Rk minus 1. So the two terms I talked about, and then we have this inner product squared divided by the L2 norm squared of A of V of K. Okay, so now we have an upper bound. Okay, a nice trick. So a nice trick, which is like to imagine that you are doing something sort of worse than what you actually do, and use this to upper bound the residual in step K, and your upper bound here will involve the residual at K minus 1. Okay, so you look at this expression here. Should we celebrate? Is it basically something that is good? Let's see. So this is the residual at step K. It is upper bounded by the residual at step K minus 1 minus a non-negative quantity. Okay, so basically what can we conclude from here? So this sequence is what? What should I write here? Is non-increasing. Perfect. Non-increasing. Which is a good sign. It's good. So basically the residual is, it remains the same or it gets lower. Okay, it remains the same or it gets lower. And actually it gets lower because, remember basically how you obtain V of K? V of K is the argmax of basically you take a Q like this and Hermitian of R of K minus 1 divided by the L2 norm, right? So you basically, you get the maximum guy here. Okay, so I mean, if the maximum guy is 0, okay, if the maximum guy is 0, it means that all the remaining columns in the matrix are like orthogonal to the current residual. Okay, and typically this will not happen. But so again, like there's good news, bad news. The good news that you basically have at least that the residual is non-increasing. But remember, in a homework problem we talked about this. Like we analyzed before the gradient descent algorithm. So the residual is like sort of the error, like the difference between what you have and what your model or your approximation. The fact that the residual is let's say even strictly decreasing, it may be strictly decreasing, but not really going to its minimum possible value. right? So this was like a tiny homework problem. And again, like it's an idea that you should have in mind that perhaps like the minimum should be like 0, but you are if you have a sequence 1 plus 1 over n, it's strictly decreasing, but it is not decreasing to 0. So this is good news, but it's not again like telling you that there is convergence. Okay, and also perhaps it's a digression, but it's also nice to keep in mind that there are some algorithms in which like stochastic gradient descent, in which at some steps actually the residual or the error may actually increase, and eventually you will have convergence. Okay, so perhaps like as an intermediate step, you may get an increase in the residual, but eventually it will converge. So like getting something that is so you may get something that is that perhaps is increasing at some steps, but this should not like give you the impression that there is no hope of convergence. There may be some oscillations, and then after that there will be convergence. Okay, so you need to make sure like to make the correct like conclusion. Okay, so the correct conclusion, we need actually to show that there is convergence, and so what we did right now is not enough. Okay, so we will analyze this RK minus 1, and what we will do is it is the minimum of this problem, and again we least squares now much better than I do, so you basically can get the solution, plug it in, and if you plug in the solution and expand the L to norm squared, you find that you can write down this L to norm squared as B Hermitian multiplied RK minus 1. Okay, now what is vector B? Well, the general case, the very general case, despite the fact that this is like sort of an overkill, and typically your matrix A will be chosen such that this will that this general case is not actually the case in your problem, but just for fun, I will assume that actually vector B has two components. One of them is in the range of A, and another component that is not in the range of A. So again, typically matrix A will be chosen, such that basically the range of its columns is the whole n-dimensional space. But let's suppose that for some reason that actually B has a component here. So basically this is more general than what you have in the homework, and it's easy. Like what you have in the homework is the special case in which actually B is in the column space of A, and so this guy is 0. You can just, if you are annoyed by this guy, you can just put it to set it to 0 at the end. Okay, so B has a component that is in the range of A, and another that is not in the range of A, and basically beta, which is basically the vector of coefficients, it comes from a least squares problem. Okay, so these are the coefficients to write down B in terms of the columns of A, and here the minimization is over all the columns of A taken together. Okay, so beta again is the minimizer here. It's not A. You do not here select anything from A. It's basically you use all columns of A. Okay, so B tilde, which is A beta, is the closest vector to B in the column space or in the range of A, and B0 is basically the remaining part of B that is not in the range of A. So what we will do is we basically will try to upper bound these two guys. And so this guy here, so we proved that RK minus 1, the L to norm squared, is equal to B Hermitian R of K minus 1. So what you will do is that you will take this B and write it as B tilde, which is the component of B in the range of A, and then you add B and minus B tilde, Hermitian, RK minus 1, and then you split this into two components. Okay? Let's take this first component. So what is B tilde? B tilde is A multiplied by beta. and so B tilde Hermitian is beta Hermitian A Hermitian, and this is R, and this is RK minus 1. Okay, and so basically, if you look here, what is this thing? So this is the column 1 of matrix A Hermitian multiplied by RK minus 1, and this and then the second column Hermitian RK minus 2, and then the third column RK minus 1, sorry, and then so this is like a column vector, A Hermitian multiplied by R, and then there is here beta 1 conjugate, beta 2 conjugate, beta 3 conjugate. So this is like an inner product, and you can write it in terms like this: bit summation L from 1 to M, which is the number of columns in matrix A, the nth column Hermitian RK minus 1, and then we will basically insert this L to norm and divide here by the L to norm. We will assume, of course, that we are not including an all zero vector in the columns of A, and then what we will do here is we will upper bound, so we will upper bound this guy by the triangle inequality, and so the triangle inequality will basically we have an upper bound which is the magnitude of this and the magnitude of that term here. Okay. Okay, then what should we do? Now you can show using the least square solution that basically whenever the index L is in Sk minus 1, whenever the index L is in Sk minus 1, then basically this inner product is equal to 0. Okay. And so there, whenever L is in Sk minus 1, this is 0. And now, if L is not in Sk minus 1, then this inner product can be upper bounded by this inner product here with AVK, because by definition we choose the new index or the new index for the column V superscript K to be the maximizer. We choose it to be the maximizer of this inner product here. Okay, and so basically what the trick here is that whenever L is in Sk minus 1, those are zeros, and whenever L is not, then those are basically upper bounded by and then we can replace this L by Vk. And so this is basically the way to go, that we will upper bound this term here by AVK, and the remaining summation, we can actually, you can say, okay, why this summation is from 1 to M, we should exclude basically Sk minus 1, not a problem. I mean, this is an upper bound, and so we can just keep the number of terms equal to M, and the remaining terms after basically getting this outside as an upper bound here will be this summation. Okay, so this will be called epsilon. This is an upper bound. This is an upper bound on this term here. Now, what about the other term? So the other term is B minus B tilde. So this is like B. This is B0, which again, this is non-zero if there is a component in B that is not in the range of A, and this is an inner product. So it is very tempting to upper bound it using the Cauchy-Schwarz inequality. So you can upper bound by the product of the L2 norms, and then you can use this inequality that the product Q1 Q2 is less than or equal to half Q1 squared plus half Q2 squared. This is simply to convert this product into a sum. Okay, so now we have an upper bound on this term, and we have an upper bound on that term. So now we have an upper bound on basically RK minus the L2 norm squared of RK minus 1. Okay, and we can rearrange the terms. So this guy here is lower bounded by this quantity. Okay, and basically. This guy here is this term. So what we are trying to do is that, we have this term here. We want to upper bound, okay, and so we have a lower bound on this guy. With the minus sign, we have an upper bound. Okay, so if you multiply this thing by a minus, both sides will be multiplied by a minus, and we have an upper bound, which we can then, okay, use yeah, to get this result here. Okay, so we obtain. So this is actually our result after we subtracted this this and that from basically both sides of the inequality. Okay, this quantity here, it's the difference between b and b. Remember that b is b tilde plus b0, and b0 is not in the range of a, and so basically this term here is what? And remember, how do we choose beta? So b tilde is a beta, and beta is the argmin of a minus of b minus a gamma over gamma. Okay, and so this is beta is the minimizer of this quantity, and we try to basically minimize. Here we are minimizing using all columns of A. Now the difference, so basically the once you get the optimal gamma and plug it in, you will get a number. This number, you cannot go below it when you do minimization. Do you agree? Right. So basically the idea is that this b minus b tilde is basically the least possible using all columns of A. While in an algorithm like orthogonal matching pursuit, we do not really use all columns, right? We start by using a column, then a second, and so on, and we keep track of the residual, and we can stop after reaching a maximum number of iterations, or once the residual is below a certain value, we simply quit. Okay, so the residual, so suppose that you let this algorithm to run and use all the columns in A. In that case, will you reach 0? Well, you can never reach 0 if B has a component that is not in the column space of A. So basically the residual, so this is the minimum possible value of the residual. So this is minimum possible value of the residual using all the columns of A, and this is 0 if B is in the range in A, which is the case of interest in practice. Okay, then basically if you define this difference between the residual at the kth iteration and sort of the minimum possible residual that you get if you use all the columns of A, so you will design this phi of k to be the difference, then now you have sort of an inequality that looks like this. Okay, I will leave the steps to you, but this inequality can be solved using induction to show that. Okay, so we can use induction to show that phi of k is less than or equal to basically d over k plus 1. So this parameter here, it's 4 psi squared and divided by k plus 1. Okay, and so you can see here the argument, and so basically this is what we have. Okay, so again, it's sort of a nice thing. So typically, like, we solve difference equations. Like, so on the left hand side we have something that is of k, and the right hand side it's k minus 1. So this is like sort of a difference inequality. Okay, and again, like here, the idea is that we will try to say, okay, can I write phi of k as less than or equal to some explicit function of k? And again, using induction, you can show that you can use this inequality here to write that phi of k is less than or equal to this constant d divided by k plus 1. Remember, phi of k is this guy here, and so the residual is always less than or equal to, and then we have this guy. So what is this guy? Okay, this guy again is, suppose that you are solving the very general problem, and B basically can be written as a sum of two components, and one component is non-zero and is not in the column space of A. In that case, this component will be like sort of a lower bound about what the residual can be. And so don't forget that this quantity here is the minimum of B minus A gamma L2 norm squared, where gamma is, so if A is n by m, so gamma is Cm by 1. And here we are using all columns of A. All columns of A. Okay, and if basically it may be the case that you can, if vector B is in the range of A, that's it, and this guy will be 0. So the more interesting term is this term here. So there is some positive quantity, and this positive quantity will depend on beta, and it will depend on the exact, basically, columns of matrix A. So there is a positive quantity, and now we have some k plus 1. Okay, so this means that the difference between rk squared minus b tilde squared, this is upper bounded by something that decays as 1 over k. So more and more iterations, right, you can make this thing as small as you wish. By increasing k, you can make this thing as small as you wish. And in the limit as k goes to infinity, this will be equal to 0. So basically here, we have convergence to the least possible value, which is this quantity, which can be 0 if B is in the range of A. And actually, we know the rate of convergence. It is basically like 1 over k. Again, you can decay as 1 over cubic root of k. You can decay as 1 over k squared. But here, like, it's 1 over k. And proofs like this, again, are very important, and they gives you, like, basically guarantee about what you should get in your algorithm. And that's the reason, like, your algorithm sort of worked. The residual would just keep getting smaller and smaller. Of course, like, in practice, you will not, like, wait for it to be 0 again. Like, typically, you will have one of two stopping criteria, a maximum number of iterations. So basically, if convergence for some reason is slow, you just need to move on, okay, and just quit after a certain maximum number of iterations, or basically if the residual is less than some quantity, you are happy and you just quit, and basically, you will use those columns of A for further purposes. Okay, and so here, again, why don't we use just B tilde? The problem is that if you solve this optimization problem, vector big gamma will typically be a non-sparse vector. It will be a non-sparse vector, full with, it will have many components that are non-zero. But the way the orthogonal matching pursuit is like sort of, we try to pick a subset of the columns of A that are, enough to basically represent vector B. Okay, so this is another example, in this course about convergence and the rate of convergence, will we have another example? It depends on what, the remaining part of the course. But this is, hopefully that this was like, will convince you why basically program 2 or basically the second algorithm was working in your homework. Okay, so now let's move to renewal processes. Any questions? Okay, so renewal processes are so here the focus will be one-dimensional, a one-dimensional renewal process, and it is a special case of a so-called counting process or arrival process. And what we have here is that we have a process n of t, and so n of t is a non-negative integer, And we typically start our system at t equals 0 and n of 0 is equal to 0. And n of t is basically a counter. It counts the number of events or arrivals on the interval from 0 to t inclusive. So t is included. Okay? And the arrivals, or events are sometimes called points, and sometimes they are called renewals, and who knows what else they are called. Okay, so I mean, they have several names, but the idea is that in one dimensions is that you have a 0 and you basically go to infinity, and then there are basically points or events that will basically take place. You assume that at the beginning nothing happened, n of 0 is 0, and then you start getting arrivals. Okay, so those may be customers arriving at a certain, a certain queue or a certain service station. Those may be packets arriving at some, basically router in a network. Many things can be modeled using, basically an arrival or counting process. So what makes a renewal process a renewal process? So basically, what again, like when you define something like this, you don't want a very general definition that is sort of will make things mathematically intractable. So what should we assume regarding basically our arrival process so that we can have some nice theoretical results that are also good in modeling reality? So basically, between each two arrivals, there is an interarrival time. Okay, so U1, there is no arrival at 0, but basically U1 by I will just say that it's the first interarrival time, despite the fact that it is the first arrival time, right? Because there is no arrival at 0. Okay, so U1 is the time of occurrence of the first event, or it's the time of the first point, or it's the basically the coordinate of the first occurrence. And then between the first and second, there is basically U2, then there is U3 between these two guys, and then there is U4, and then there is U5. And so again, those are called the interarrival times, despite the fact like the first time is the first arrival. And in a renewal process, basically, the interarrival times are IID. So this is the main property of renewal processes, that the interarrival times, U1, U2, U3, and so on, this is a sequence of random variables, okay, and basically those random variables are independent and identically distributed. If you choose those random variables to be exponential, then this will be the special case of a Poisson process. So the Poisson process is basically a special case of a renewal process, which is a special case of an arrival or counting process. Now, the time between so T1 is the time of the first arrival, so T1 is equal to U1. T sub 2 is the time of the second arrival, and so it is equal to U1 plus U2. T3 is the time of the third arrival, and so this is U1 plus U2 plus U3, and so on and so forth. So Tk is the summation from j from 1 to k of Uj. Interarrival times are random variables, and we can choose any distribution for these. In our course, we will focus on the case in which the interarrival time is an absolutely continuous random variable. So it is characterized by a PDF that is given as small f sub u, and it is a PDF for a non-negative random variable. In fact, we will assume that basically the interarrival times are strictly positive. It is known in probability theory that for non-negative random variables, sometimes it's very convenient to use the Laplace transform. And this is what we will do here. So the Laplace transform is basically the expectation of e to the minus su. S is generally a complex parameter. Okay, and so basically, expectation e to the tu, small tu, that's the moment generating function. But rather than using t, which is real valued, we will use minus s, and s is complex valued. And this is the Laplace transform. And basically, because our random variables here are continuous, this is the expectation written in terms of the PDF. Now, you can see easily that if you choose the real part of this parameter s to be strictly positive, then the magnitude of the Laplace transform, and the Laplace transform here is denoted by big phi. So in this course, you have small phi, so this is characteristic function, but this is Laplace transform. The magnitude of the Laplace transform will be less than 1. The CDF corresponding to the BDF is denoted by big F, and we will assume that basically FU of 0 is 0. In other words, we assume that the probability that the interarrival time is equal to 0, that this probability is equal to 0. Okay, so the probability that the interarrival time is 0 is actually, it happens with probability 0. And by doing this, we are sort of prohibiting simultaneous arrivals. So we do not allow like an arrival that is followed by another arrival with a time difference that is equal to 0. So our point process or our counting process is sometimes called symbol. So symbol, which means at an instant of time with probability 1, we just have one arrival. We do not have 2 or more arrivals at the exact instant of time. From the Laplace transform theory, basically, if the CDF is the integral of the PDF, and so basically the Laplace transform of the CDFs, you take the Laplace transform of the PDF and you divide it by S. So the Laplace transform of the CDF will be big phi over S, and 1 minus the CDF, the complementary CDF, it will be 1 minus big phi over S. If you do not need to basically review the Laplace transform. So basically here we will learn like a couple of useful things, and you just use them. Basically, the weakest part in this part will be the use of the Laplace transform. We will try to be rigorous when we do everything except like when it comes to the Laplace transform. We will take many things for granted. Otherwise we'll be trapped in the Laplace transform theory, and it is not what is intended in this part of the course. We will assume that basically we have a finite first moment. The first moment can be plus infinity, and later when we study Markov processes, it will be actually a must that we deal with basically random variables with an infinite first moment. Again, from the Laplace transform theory, basically the expectation of the interarrival time can be obtained by differentiating the Laplace transform. So you can differentiate the Laplace transform once, put a minus sign and put s equals 0, and this will give you the first moment. Or you can do it like this. Okay, so again, you can take it for granted that if you have a Laplace transform and if the first moment is finite, you can get the first moment, you take the Laplace transform, 1 minus the Laplace transform divided by s, then you take the limit as s goes to 0. This will give you the first moment. In the Laplace transform theory, there is a very useful property called the final value theorem, and it tells you that suppose that you have a function and it depends on t and its Laplace transform is big G of s, Suppose that you are interested in the limit of this function as t goes to infinity. And suppose that you can easily obtain g of s. So how can we obtain this limit here? You have two options. One of them is to take the inverse Laplace transform, g of t. So you have the inverse Laplace transform, and then you take the limit as t goes to infinity of g of t. But the inverse Laplace transform may not be feasible. You cannot, for example, get it in closed form or something like this. So the final value theorem is very nice, and it tells you that under some conditions, you do not need actually to do the inverse Laplace transform. What you can do is that you can remain in the S domain. You can take your g of s multiplied by s and then take the limit as s goes to 0. And this will give you the required limit. Now, this is not always true. It is always, it is true under some conditions. The problems and the exercises that you will face in this course will have those conditions satisfied. So basically, if you find in any problem that the way to go is to apply the final value theorem, go for it. I will not use any trick in which you use it and it is not actually valid. Okay, so the focus is basically renewal processes, not the Laplace transform itself. The Laplace transform of an integral you divide by s. The Laplace transform of a derivative is basically that you multiply by s and then you subtract the initial value. If the initial value is 0, then the Laplace transform of the derivative is the original Laplace transform multiplied by s. Finally, the Laplace transform of a sum of independent random variables, it has the same nice property that we have for the moment generating function and the characteristic function, namely that the Laplace transform of a sum of independent random variables is the product of the Laplace transforms. So it is one feature that makes the Laplace transform very attractive. So having a sum of random variables, again, sum of random variables, if you like, if you do distributions, you will have to do repeated convolutions. But if you use something like the Laplace transform, you just need to just multiply things. Okay. So let's first, when you study an arrival process, so a Poisson process. So Poisson process, in a Poisson process, basically with parameter lambda greater than 0, then basically the number of arrivals between 0 and t, so number of arrivals on 0 and t, that this number of arrivals, right, this number of arrivals, basically it is Poisson with a parameter which is equal to lambda multiplied by t. Okay, so this is Poisson. Now, what is a we know now that renewal processes are basically like Poisson process, but you allow the interarrival time to be general. Okay, so that's the idea. Rather than just sticking to the exponential distribution, now your interarrival time can be anything. And for the purpose of this course, actually we will focus only when the interarrival time is a continuous random variable. Okay, so what is the PMF? Okay, what is the PMF of n of t for a general renewal process? So one way of deriving the PMF is to make use of this very nice equivalence. N of t greater than or equal to small n if and only if big T sub n is less than or equal to t. So remember that big T of n is the time of the nth arrival or nth event, and big T of n is equal to u1 plus u2 up to un. So I am saying that these two events are equivalent. So if at time t the number of arrivals is greater than or equal to n, it must be the case that the time of the nth arrival is less than or equal to t. Again, if you measure the number of arrivals at time t and you find that it is greater than or equal to small n, it must be the case that the nth arrival has occurred at a time that is less than or equal to t. The converse is true. If the nth arrival occurred at a time that is less than or equal to t, then if you count the number of arrivals at time t exactly, then the number should be n or more. It should be greater than or equal to n. So these two events are exactly the same. So the probability that big N of t is greater than or equal to small n is exactly the probability that the nth arrival time is less than or equal to t, and the nth arrival time is the sum of those NIID interarrival times. Okay, so basically this is this is the CDF of t of n, and I will denote it at f sub n of t. So f sub n of t is really the CDF of t sub n. Okay. So now, according to the equivalence between these two events, the probability that the number of arrivals at time t is greater than or equal to small n is equal to this. Is equal to the CDF of t of n evaluated at t. Now rewrite this this equality, replacing n by n plus 1, and then. So basically, this is the probability that n of t is greater than or equal to small n. This is the probability that n of t is greater than or equal to n plus 1. So the difference between these two guys, so basically this is the difference. The probability that n of t is exactly equal to small n is the probability that n of t is greater than or equal to small n minus the probability that n of t is greater than or equal to n plus 1. So the difference between these two guys will give you the probability that n of t is exactly equal to small n, and hence this PMF is equal to the difference between these two CDFs. So this is the CDF of Tn, and this is the CDF of Tn plus 1. And don't forget that Tn is the sum from u1 up to un, and Tn plus 1 is the sum from u1 to un plus 1. Okay, so the PMF, and if you of course account for the special case, of what is the probability that n of t is equal to 0, you know, probability that n of t is equal to 0, it means that it is the probability that we have no arrivals till t, which is the probability that u1, the time of the first arrival, exceeds t. So that's 1 minus the CDF of the interarrival time. And once n is 1 or 2 or 3 and so on, basically the PMF is the difference. Okay, so now see what we are talking about. We are talking about things that are not easy at all. This quantity is the CDF of a sum. That's bad, right? CDF of a sum is not something that is easy to compute. Okay, so keep this in mind, that the general PMF of a renewal process is typically something that we cannot actually compute. Okay, so that is the PMF, and whenever you study renewal processes, it's always a nice exercise, like to check whether your result as a special case will give you what you know about the Poisson process, right? So in a Poisson process, basically the interarrival time is exponential. So the interarrival time is exponential lambda. And now, what if we apply, what if we compute this for a renewal process in which the interarrival time is exponential? So we need to know what is the distribution of NIID exponential random variables. So you can do this via repeated convolutions. You can do this via Fourier analysis or the Laplace transform. You can do this via induction. You can do this in any way of your choice. And basically you get that the CDF is equal to this integral here. So this is the CDF of the sum u1 plus u2 up to un, and the PMF is basically the difference between the CDF Fn of t minus Fn plus 1 of t. Okay? And the nice thing about basically this difference is the following, that you can do one step of integration by parts and apply it here. And when you do so, you will get two terms. One term will be exactly like the first integral, but with a different sign. And so these two guys cancel, and the remaining term, after doing the substitution of the upper and lower limits of integration, will give you the Poisson PMF. Okay, so it's a nice check. The general case again is difficult because you will need to deal with monsters. I am saying monsters, not in a little, not actually in a figurative sense. This thing is a monster, so it's sort of a literal sense. This is bad. CDF of, yes, the guys are IID, but even the CDF of NIID random variables may not be nice at all. Okay, so we can use the Laplace transform. Laplace transform again. What do you get? What do you guess is the benefit? So yeah, now you can see that in the analysis of a renewal process, asking the very first question that comes to mind, what is the PMF of n of t? You face the CDF of the sum of IID random variables. Okay, so perhaps it is like sort of better to do things using basically the characteristic function or moment generating function. Here we will use the Laplace transform. Again, for non-negative random variables, people typically go for the Laplace transform. Okay, and what is the Laplace transform of this thing? So remember that the PDF itself, it has a Laplace transform, which is phi u of this. Okay, and so the PDF of basically the PDF of u1 plus u2 up to un. Okay, so what is the Laplace transform of a sum? So the Laplace transform of a sum, this is the nice thing, you just multiply the Laplace transforms, and because those guys are IID, you just need to take the Laplace transform of one of them and raise it to the power n. And finally, CDF, which is the integral of the PDF from the theory of the Laplace transform. Again, we will take this for granted, then we divide, so we take this to the power n, and then we divide by s. Okay, so here we are exploiting the fact that by definition in a renewal process, the interarrival times are basically a sequence of IID random variables. Okay, so this is the PMF. Okay, and again, it's the first question that comes to mind. Now, a quantity of interest in the study of renewal processes is the first moment of n of t. It's so-called the renewal function, the expectation of n of t. But before doing that, any questions? Okay, so the renewal function is the expectation of n of t. And the expectation of n of t, again, n of t is an integer valued, it's a non-negative integer valued discrete random variable. And so we know, or you know from a previous course, that basically the expectation can be written in terms of, I think perhaps we did it in one homework problem or something like this. We can write down the expectation in terms of the complementary CF. So, and remember those guys? Remember that we have that the probability that n of t greater than or equal to small n is exactly equal to the probability that u1 plus un is less than or equal to t. So that's basically the CDF of those guys, which is denoted by Fn of t. So you have this summation here. So n of t is given by this sum. So now we have basically a double level of, of scary things. So we have again, we have Fn of t itself is a not nice quantity at all. It's the CDF of the sum of NIID random variables. And now we are taking those guys and we are summing them from 1 to infinity scale. Okay, so, and whenever you see an infinite sum, oh, I mean, then you have all those questions. Does this sum even make sense? For any finite value of t, does this sum converge? Who tells us that even the first moment of n of t exists as a finite real number? Perhaps it's a plus infinity, and so on and so forth. Okay, so once you talk about the first moment of a random variable, and now it is expressed as an infinite sum, then all these questions must come to mind. How are we sure that this thing is finite? Okay, before actually sort of arguing for this, let's do the check that I told you about, which is like, it's always, a matter of curiosity. Okay, I mean, so if I apply this to what I know about the Poisson process, will it give me what I expect? Okay, for a Poisson process, again, this is the PDF of the sum of NIID exponential lambda random variables, and Fn will be the integral. And this integral, I think it has a formula with a summation, but we don't need it. Okay, so what if you plug in this integral, put it here, and because our stuff is non-negative, by Tonelli, we can actually interchange the order of integration and infinite summation. And so you can bring the infinite summation inside, and when you bring the infinite summation inside, you will find that you have the Taylor series for an exponential. And the Taylor series of the exponential will give you an e to the lambda u term that will cancel this e to the minus lambda u term, and you find yourself basically integrating from 0 to t1 du multiplied by lambda. So this will be t multiplied by lambda t, right? So we know, you know from a Poisson process, okay, that the expectation of n of t, the number of arrivals, basically up to time t with t included, that this thing is equal to lambda t. Okay, so we get our result here, but again, there are those questions. Are we sure even, so okay, so for a Poisson process, for every finite t, the first moment is finite. Is this like a general thing or not? So, several years ago, I used basically to study this summation and show that actually it converges, okay? But then, thinking about it, I found it in some reference that actually it's a nicer result, that all the moments of n of t are finite for a finite t. So long as you assume this thing here, that basically the interarrival time is strictly positive with probability 1, then it is not just that the first moment is finite, actually all the moments. So if I write down expectation of n squared of t, I am guaranteed to get a finite number. Okay, n cubed, n to whatever power of your choice. Okay, so let's go for the general thing. If you can do something general, why just justify this first moment, while you can actually justify basically all moments in just one proof. Okay, so the idea here is the following: that if we have a strictly positive random variable, which means that this random variable is, the probability that u1 is zero, then, so here is the idea or the trick, is that there exists positive alpha such that the probability that u1 is greater than alpha is strictly positive. Okay, so the idea that if you know that there is a random variable that is positive, will almost surely, then there is always some value alpha such that the probability of u1 greater than alpha, that this probability, you can always find this alpha making this probability strictly positive. And how can we show that? Well, you can do it by contradiction. Okay, by contradiction, like you challenge this. You say, no. For every positive alpha, actually the probability that U1 greater than alpha is equal to 0. But if you assume this, then you can use continuity of probability to show that the probability that U1 is strictly positive is 0. And this contradicts our assumption that the probability that U1 is strictly positive is actually taken to be 1. Okay, so because of that contradiction, there is always guaranteed to be some positive alpha such that the probability that the interarrival time, I put here U1, but remember that the U1, U2, and so on, this is an IID sequence, right? So basically, each one of them, it has the exact same distribution. Okay, so what we will do is something that is so cool. What we will do is that we will take n of t, and we will upper bound n of t by a random variable that is known to have finite moments. So the trick here again is that I will take n of t. Once you fix a t, that's a random variable, giving you the number of arrivals from 0 to t. Now n of t, if I can upper bound it by a random variable that is basically a famous random variable, and it's well known that that random variable has finite moments of all positive integer orders, then n of t itself must have, basically finite first moment, finite second moment, finite third moment, and so on and so forth. Okay, so that's basically the trick. So I will take n of t and I will rewrite it in this nice form. So n of t is the maximum of values of n. So n is a natural number, n is 1, 2, 3, such that t of n is less than or equal to t. So you need to think a bit about, basically this definition. So n of t is number of arrivals on 0 to t, right? So I'm claiming that you do this. You have your arrivals, right? You have your arrivals. What you do is that you examine the time of arrivals, T1, T2, T3, T4, and so on. And basically, so long, you start increasing n till you violate this inequality. So the largest n for which this inequality is satisfied, it means what? I mean, this inequality means what? The nth arrival happens at a time less than or equal to t. Okay, so again, n of t, it is basically the maximum. So n of t, it is the maximum. N is a natural number such that t of n, it's the number of n such that the maximum guy such that t of n is still less than or equal to t. It's the maximum n such that t of n is less than or equal to t. So suppose that t is here. Okay, suppose that t is here. Okay, so t1 is less than or equal to t. Okay, great. So is t2 less than or equal to t? Great. Is t3 less than or equal to t? No. So what is the maximum n for which tn is less than or equal to t? 2. And really here, n of t is exactly equal to 2 in this example. Okay? Now, t of n is the sum of NIID, interarrival times. And basically, here is another nice trick. We will basically lower bound u of k. So I will take u of k, right? So this is the kth interarrival time. So this is the time duration between arrival k minus 1 or event k minus 1 and arrival or event k. Now, it is greater than or equal to u of k, and then you put an indicator function, a strategically designed indicator function with u of k greater than alpha, positive alpha. right? Because basically this indicator is 1 or 0, and so this thing here is either u of k or either 0. Okay, so again, so here u of k is multiplied by 1. Now you replace the 1 by an indicator function that will be 1 if the condition u of k is greater than alpha, 0 otherwise. And then you have another step of lower bounding and say that this is greater than or equal to alpha, and then indicator u of k, right? Is this true? Do we have this inequality? Yes. If the indicator is 0, if the condition is violated, you have 0 less than or equal to 0, which is fine. Now, if the indicator is 1, then uk is greater than alpha, which means that uk is greater than or equal to alpha. So this inequality is true. So basically what we will do here is that we will lower bound uk by this thing here, by alpha, indicator uk greater than alpha, right? So from this inequality, okay, sum both sides from k equals 1 to n. So you have basically that summation k from 1 to n, u of k is greater than or equal to summation k from 1 to n. Now with alpha, indicator uk greater than alpha, right? So now if the sum of the u's is less than or equal to t, and the sum of the u's is greater than or equal to this sum, okay, then it must be the case that this will also be satisfied, right? So if for a certain n, basically we choose the summation of the u's to be less than or equal to t, then it must be the case that this is less than or equal to t. This can be less than or equal to t while this is not, okay? So what we can say from here is that we can upper bound, so the maximum n is less than or equal to the maximum n here, replacing this summation by this summation. Why? Because this summation here is less than or equal to this guy. Okay, so basically, if for a certain n this inequality is satisfied, we are sure that it will be satisfied downstairs. The converse is not true. So it must be the case that the maximum of the over the natural numbers n, such that this inequality is satisfied, is greater than or equal to basically the term that is equal to big N of t. So that's one step of our bounding. Okay. Then we will do another thing, which is that if this summation is less than or equal to t, then it is also less than or equal to, I will put a quantity here, which is t over alpha ceiling multiplied by alpha, right? Because this quantity, if you take t, if you take the ceiling of t over alpha and then multiply by alpha, you get something that is guaranteed to be greater than or equal to t. So basically, if this summation is less than or equal to t, then it's guaranteed to be less than or equal to again this thing here, which again it's not very clear why we will do something like this. It will be clear in a minute. So we replace t by the ceiling of t over alpha multiplied by alpha. So here is the idea. Now you have an alpha on the right hand side of this inequality. So now we have an upper bound on big N of t. We have alpha here, we have alpha there. So we can just eliminate the alpha. Okay, remember what is the idea of this alpha, that if you have a random variable that is strictly positive with probability 1, you can find a strictly positive alpha such that the probability of u1 greater than alpha is strictly positive. So alpha is strictly positive, and you can eliminate it from both sides. Now if you eliminate it from both sides, now we have a summation of indicators which go from 0 to 1, which are either 0 or 1, and then we have a floor function, a ceiling function, which is an integer value. Okay, so again, what is the benefit of doing something like this? So the benefit is summation k from 1 to n, indicator uk greater than alpha, is a sum of zeros and ones, depending on whether uk is greater than alpha or less than alpha. If the indicator, if the inequality is satisfied, we have 1. If not, we have a 0. So that's a 0-1 sum. That's a 0-1 sum. It's different from the original sum, in which basically we are summing the interarrival times. And actually, in this course, we take them to be absolutely continuous random variables. Now we have a sum that, basically each term is 0 or 1. Moreover, what we have is that here we have a ceiling. We have a ceiling of so we take t, which can be any parameter of our choice. We divide it by alpha, which is something, it depends on basically, we choose it. It will depend on the exact distribution of u, but it exists once we assume that u is strictly positive with probability 1, and then we take the ceiling, and so that's another integer. Okay, so we ask, so this upper bound is what? We are having a sum of zeros and ones, and we ask ourselves, for what n this sum will reach the integer value, which is ceiling t over alpha. Okay, we are asking this. So in fact, so again, think about it. We are summing zeros and ones. We basically, we need, we want the maximum n that makes you reach this number. So you keep increasing n, increasing n, increasing n, till you reach this number. Now, because after upper bounding, and because of this very smart choice of the upper bound, so that we have an indicator here, and this guy here is an integer, now this maximum n that will make this summation, basically remain less than or equal to basically this integer value ceiling t over alpha, is exactly equal to the value of n that achieves equality between this summation and the ceiling of t over alpha, right? So again, you have a threshold, and you have basically numbers between 0 and 1, and you keep summing, and you want the maximum n such that you remain less than or equal to the threshold. This is, since now you are summing zeros and ones, and the threshold is an integer, it's the ceiling of t over alpha, then basically the maximum n that is in the upper bound on n of t is exactly the n that achieves this equality, such that summation k from 1 to n, indicator u of k greater than alpha, is exactly equal to this t over alpha. So again, so see, the one who invented this proof is like, again, you wanted basically something, a summation of integers, the easiest will be zeros and ones, and on the other side, rather than having less than or equal to some arbitrary real number, now you have an integer, and so now it becomes a matter of, the maximum is just equal to this. Okay, so now n of t is less than or equal to this thing here. N, what is n? It's the n that satisfies this, that summation k from 1 to n, indicator uk greater than alpha, is equal to the ceiling of t over alpha. And this random variable I will call big Z. So what is big Z? Again, think of it like this. So you have a certain target, which is ceiling t over alpha. What you do that you ask yourself, what is the value of n such that the sum of the indicators will make me reach this specific value. Okay, so the indicators can be 1 or 0. They are 1 with probability, the probability of the event UK greater than alpha, which is a positive probability. And the probability that the indicator is 0 is 1 minus that probability. Okay, so we can imagine again that we have Bernoulli random variables, and we are basically, it's like you are doing n experiments, and your objective is to get ceiling T over alpha successes. Okay, so of course the minimum number, what is the minimum n? The minimum n will be ceiling T over alpha. Okay, and generally you can compute this probability. Okay, so here I will give you, the probabilities in terms of combinations, and so it's like sort of, I can like, you can solve this problem in an introductory course in probability. So again, how many trials, okay, in which like you can succeed with a certain positive probability, fail with 1 minus that probability, till you accumulate a specific number of successes. Okay, so which means that your last trial will be a success. And then before that, among the first n-1 trials, we will have this number of successes, and basically n-1 minus ceiling T over alpha minus 1 will be the number of failures. Okay, so now, there are 2 ways to go from here. I basically, here I pretended as if we know nothing about this random variable, but this random variable is actually a famous random variable. It's called the negative binomial distribution. Okay, so because it's if you think about it, it's a basic probability question. If you have Bernoulli trials in which you can have success or failure, 0 or 1, head or tail, then you ask yourself, what is the probability that I need n trials, and in those n trials, my last trial will be the nth success. So again, this is something that is well studied in probability, and here is the good news. The random variable, basically the so-called negative binomial, it has finite moments. All its moments are finite. Okay, and so n of t has finite moments. Okay, so that's basically the story. Okay, so you can show it by actually computing the moment generating function of basically this z random variable, and you can show that the moment generating function is finite on an open interval about 0, and then we have this theorem that if you have a random variable with a finite moment generating function on an interval about 0, then all the moments are finite. And since all the moments of z are finite, and basically n of t is upper bounded by z, then all the moments of n of t are finite. Okay, so expectation of n of t is like, you should not fear doing something like that. Okay, so this thing is defined, and n of t is finite for every finite t. Okay, and so n of t is the expectation of n of t, and it is basically, lambda t if we talk about the special case of a Poisson random variable. Okay, now we want to write n of t in sort of a useful form, and so we will basically do this trick that is useful in Poisson and renewal processes, that is called conditioning on the first arrival trick. Okay, so there are problems that appear to be very difficult, but you can easily relatively speaking, solve them by conditioning on the time of the first arrival. And so basically we will do this trick, and we will write down an integral equation for the renewal function.